Only using bamboo, Indonesia has solved an infrastructure puzzle that had stalled its economy for decades and redefined what's possible for a G20 nation. Faced with unstable, fractured coastal terrain along the northern shores of Java, Indonesian engineers turned to an unlikely solution: 10 million bamboo poles. A material often dismissed as cheap and fragile was used to build 27 kilometers of national highway at just 1/5 the cost of a traditional expressway. This wasn't just a functional road. It was a bold challenge to the world's assumptions about sustainable construction. So here's the question. In an era dominated by concrete and steel, why would a G20 country bet its infrastructure future on bamboo? And can a material prone to rot and lower in compressive strength really replace reinforced concrete? In today's episode, Massive Minds takes you deep into the heart of the Semarang-Demak Highway, one of Indonesia's busiest coastal corridors, to test the true limits of this remarkably resilient plant. Picture a city where the ground beneath your feet disappears by nearly half a foot every single year. There are no storms and no warnings, just seawater creeping into the living rooms of millions. Trade stops, cargo ships turn away, and every high tide becomes a countdown to a looming disaster. This isn't a scene from a far-off Hollywood apocalypse. It is the lived reality of Semarang, the capital of central Java. Semarang is sinking at a staggering rate of 15 centimeters annually. It is a slow-motion collapse, a catastrophe that remains invisible day by day until an entire district simply vanishes beneath the waves. The tragedy is man-made. Decades of uncontrolled groundwater pumping have crushed the ancient marine clay below, turning solid earth into a fragile, liquid-like trap. In the face of certain destruction, the Indonesian government took a gamble that many called a suicide mission. They decided to build the Semarang-Demak Toll Road, a 27-kilometer coastal expressway designed to be more than just a road. It was to be a massive man-made shield, a seawall built to hold back the entire Java Sea. But there was one impossible problem. How do you lay down thousands of tons of steel and asphalt on ground as soft as wet clay? How do you build a highway on a foundation that is effectively liquid? The engineers didn't look to the future for the answer. They looked to a material the modern world had long ago forgotten. They looked to the bamboo. Bamboo is not magic. It will snap, it will sink, it will rot unless you truly understand its properties and, more importantly, the weaknesses of the ground beneath it. Before a single pole touched the mud, they pierced the Semarang seabed with dozens of deep-core boreholes. They pulled up suffocating cylinders of dark marine sediment, a primordial record of a land that was never meant to carry the weight of civilization. These were slices of time, millions of years of accumulated silt that had never seen the light of day. Then came the verdict from the standard penetration test. In the world of engineering, this is the moment of truth. But for Semarang, the results delivered a crushing reality. Beneath the surface lay 60 meters of soft marine clay. To put that in perspective, imagine a 20-story skyscraper made of nothing but waterlogged silt. That is the foundation of this region. It has the structural integrity of quicksand. Attempt to build a standard highway here, and the earth wouldn't just sink, it would swallow the entire multi-billion-dollar project whole. But the earth wasn't the only enemy. While one team dissected the mud, another mapped the chaos of the water. They built a digital apocalypse, running marine hydrological simulations to calculate the crushing, sheer force of waves and the relentless pressure of tidal currents. They accounted for the heavy ground phenomenon, the terrifying moment when strong southeast monsoons turned the sea into a battering ram against the coast. They fed every nightmare scenario into a 3D model, creating a digital twin of the disaster. This wasn't just data, it was a survival map. After obtaining initial geological data, the process of processing and testing bamboo to ensure its load-bearing capacity is carried out. It's important to know that bamboo is a natural material and subject to the laws of decomposition, so the entire quantity of bamboo must pass rigorous testing standards, more stringent than any other common construction material. First, a tensile test is conducted to measure the tensile strength of the bamboo when stretched lengthwise. After passing this test, bamboo stalks are found to have tensile strength comparable to soft carbon steel, an unexpected achievement for an organic material. Next, a bending test is conducted to determine the elasticity and ability of the bamboo to recover its original shape when bent. This is a crucial factor because the bamboo layers must adapt to the deformation of the seabed, a constantly fluctuating environment due to waves and tides. Finally, there is the compression test, which evaluates the ability to withstand vertical compressive loads, accurately simulating the working conditions of bamboo when subjected to thousands of tons of sand, asphalt, and vehicles daily. However, not all bamboo meets the standards. Only mature bamboo over 3 years old, having reached maximum physical strength with a uniform diameter of about 10 centimeters, free from cracks, and a minimum length of 8–10 meters, can ensure structural effectiveness when bundled together. When these seemingly stringent requirements are met, bamboo, a material once considered outdated, has now become a promising strategic infrastructure material of the 21st century. But turning millions of quality-tested bamboo stalks into a foundation strong enough to support a coastal expressway wasn't as simple as just driving them into the seabed. Indonesian engineers developed a unique construction process where each bundle of bamboo had to be treated, assembled, and installed as a precision-engineered structural component, often outperforming conventional materials like concrete or asphalt in soft ground conditions. Instead of driving individual poles, the engineering team grouped 7 bamboo stalks into a single unit. Each bundle was tightly fastened with high-tensile nylon rope or stainless steel wire, forming what they called a super pile, a structure far more stable and resistant to torsion. This method not only increased durability, but also reduced the risk of snapping or toppling when exposed to strong coastal currents or uneven ground pressure. Once assembled, millions of these bamboo piles were transported to the muddy tidal zones off the coast of Java. There, using a combination of hydraulic pressing and ultrasonic vibration, machines gently pushed the piles deep into the clay-rich seabed. This technique allowed each cluster to penetrate the thick, silty layers without damaging its structure, forming a dense, uniform grid at a rate of 1 pile per meter. The result? A stable, load-bearing foundation that not only supports the weight of future highway structures, but also reinforces and locks in the surrounding seabed, a critical factor in regions like Java, where tidal flows and soil subsidence are notoriously difficult to manage. This remarkable blend of local materials and modern construction techniques transformed what was once considered impossible, building a highway on sinking mud into a proven engineering reality. Once the dense network of bamboo piles had been embedded into the seabed, the project moved to its next and most delicate stage, the installation of bamboo mattresses. If the vertical bamboo piles acted like pillars anchoring the foundation, then these massive horizontal mats formed the backbone of the system. Their role was to redistribute the load, stabilize the surface, and prevent the soft clay underneath from shifting or rising. Tens of thousands of bamboo combs were delivered to the site and assembled into enormous woven panels, some crafted by hand, others with semi-mechanized support right on floating barges in the middle of the bay. Each panel stretched dozens of meters long and as wide as a roadway. They were cross-woven, strand-locked, and reinforced with tension steel bars to ensure structural integrity before being lowered into the water. But a single layer was not enough. Engineers designed up to 13 to 17 stacked layers of these bamboo mattresses, each offset and interwoven with the others. Together, they formed a resilient and elastic mass capable of withstanding vertical pressure while absorbing vibrations from both ocean waves and the daily passage of multi-ton trucks. Once deployed over the forest of bamboo piles, these mattresses function like a flexible cushion, slightly buoyant, reducing sudden pressure and resisting long-term surface deformation. This was not just a measure to prevent subsidence. It was a dynamic structure able to interact with the unstable seabed below, something neither concrete nor steel alone could achieve in the unique marine environment of Java. Next came the installation of the geotextile membrane and the massive sand fill that would shape the future roadbed. First, a layer of ultra-durable polymer geotextile was carefully spread over the entire surface of the bamboo mattresses. This textile acted as an intelligent filter, preventing sand from seeping through and mixing with the underlying mud while also shielding the bamboo from aerobic microorganisms, the main culprits of natural decay in wet environments. Immediately after the geotextile was in place, specialized dredging vessels began pumping millions of cubic meters of treated marine sand onto the surface. This enormous volume of sand served two purposes. It sculpted the physical shape of the roadway and, more importantly, acted as a preloading weight, compressing the soft clay layers below and minimizing future settlement over time. To complete the structure of the expressway embankment, engineers deployed a system of prefabricated vertical drains, PVD, a breakthrough technology designed to rapidly drain moisture from waterlogged coastal soil. Think of each prefabricated vertical drains unit as a type of engineered paper straw. It has a plastic core to maintain structural shape, wrapped in a layer of synthetic fabric that draws in water. When the heavy sand fill presses down from above, it creates intense vertical pressure. This force squeezes the water out of the underlying soft clay. The fabric sheath absorbs the moisture, which then travels upward through the plastic core, escaping to the surface rather than seeping sideways into surrounding soil. Thanks to this simple but highly effective principle, the prefabricated vertical drain system accelerated the natural soil consolidation process. What would normally take 2 decades to achieve through natural settlement was reduced to just 6 to 12 months, a dramatic leap that made the Semarang-Demak Coastal Expressway not just possible, but practical. With impressive construction speed, once it passes the final load-bearing capacity test, Java's stunning highway will no longer be just a blueprint. To ensure both precision and safety, convoys of heavy-duty trucks were deployed to roll back and forth across the road surface. These simulated real-world scenarios over many continuous hours, from festival traffic surges to high-speed emergency braking in torrential rain. All the while, ground-penetrating radar, GPR, scanned deep into the structural layers, measuring deflection and identifying any weak points hidden within the bamboo, sand, and geotextile below. Only when all performance indicators fell within safety thresholds did the final phase begin: asphalt paving. Specialized asphalt mixes, engineered for high heat resistance and micro-movement absorption, were carefully laid across all 27 kilometers of the Semarang-Demak Expressway, forming a smooth, durable driving surface anchored atop layers of nature and ingenuity. And just like that, in a place once submerged in seawater and skepticism, a modern expressway was open to traffic. But it delivered far more than just vehicles. It carried new hope for coastal economies and a powerful reminder that, when modern engineering embraces local knowledge, even the softest ground can support the weight of the future. In just over a year since its inauguration, the Semarang-Demak Expressway has already transformed regional connectivity. Freight transport times between northern seaports and inland industrial zones have dropped by more than 40%. What was once a daily loss of billions of rupiah due to paralyzing traffic has been replaced by the smooth, uninterrupted flow of logistics and tourism. But this road is not merely an economic corridor. It is also a climate resilience strategy. As sea levels rise and saltwater pushes deeper inland, the same villages that once faced repeated flooding now lie behind a built-in coastal defense. Integrated directly into the expressway is a continuous dike system, shielding over 500,000 people from tidal surges, saltwater intrusion, and the looming threat of forced relocation. Yet perhaps the most remarkable legacy lies not just in what this road accomplishes, but in how it was built. For the first time, a national expressway has been supported by bamboo, a material once dismissed as too primitive, too fragile for modern infrastructure. Today, it stands as proof that when engineered with purpose and precision, even humble materials can carry the weight of a nation's future. Even after completion, the Semarang-Demak Expressway continues to spark debate. If bamboo hadn't been used, could there have been a better solution? Technically, yes. The Netherlands, for example, built the Afsluit Dike, a 2-kilometer-long seawall separating the Wadden Sea from the mainland, using millions of tons of rock and massive concrete tetrapods. It's a brute force defense, rigid, permanent, and nearly unshakable. But Indonesia faced a different equation. They weren't just fighting water. They were building within it, under tight budgets, on soft tidal soil, with materials that had to be sourced locally. And in that context, bamboo wasn't a compromise, it was a strategy. When grouped, treated, and layered with geotextiles, bamboo became more than a traditional material. It acted like a smart, adaptive foundation. It was light, fast to install, cost-effective, and surprisingly resilient when engineered properly. Of course, it's not without flaws. Its lifespan is shorter than that of concrete. But when you weigh time, cost, and flexibility, the balance tips in bamboo's favor, especially for coastal nations facing similar soil and climate conditions. So, here's the real question. If you were in charge with limited funds, soft ground, and a ticking clock, would you have chosen concrete? Or would you bet on bamboo? Tell us what your choice is in comment. With only bamboo and ancestral wisdom, Indonesia has achieved the impossible, carving a national highway through a mangrove dead zone. Without reinforced concrete or massive cranes, they prove that innovation isn't about expensive tools. It's about maximizing local resources. The Semarang Demak Highway bridges the rigid strength of the past and the fluid adaptability of the future. It isn't just a road. It is a bold declaration for a century of sustainable engineering. In an era of climate crisis, is this our way forward? Let us know your thoughts below and subscribe to Massive Minds for more engineering wonders that are changing the world.